Okay, so last thing we need to do is verify that two functions are inverses of each other. And this word verify is code for proving. So yes, we're going to do some proofs. No, it's not going to be like a geometry proof. It's an algebraic proof. Here's our proof. This is what we have to do. The functions f and g, the two equations, are inverses of each other if provided the composite f of g of x gives us x, it's called the identity, and we have to do a second part to our proof. The composite g of f of x also has to equal the identity of x. That x has to be all by itself, nothing added, subtracted, multiplied, divide to x. It's got to be a plain x for these two composites to give us the proof that they are inverses of each other. So we're actually going to work on example 9 down here together because I think it's a little bit trickier than the other two equations. And we'll do our composites here together. So the first composite we'll work on is the f of g of x composite. So remember, we start with the outside function, which is x to the fourth minus 2 divided by 5. We want to remove that x and create a pocket. So pocket to the fourth minus 2 divided by 5. And then remember, we have to fill the pocket with something, and that inside function is what fills our pocket. So into our pocket goes the fourth root of 5x plus 2. And then we're going to work on simplifying this equation. I know it looks ugly, but it's going to simplify very nicely. The thing to remember when you're doing a proof is that you have to show every step. You can't skip or combine any steps. So when we see a fourth root and a fourth power, we know that those two things are inverses. So we've cleared that fourth root. And we have 5x plus 2 minus 2 divided by 5. So I will continue my proof up here. Now that we've gotten rid of the radical symbol, we can combine like terms. Up in our numerator, a plus 2 and a minus 2 are going to cancel each other out. And what we have left is 5x divided by 5. Showing my very last step here, doing some division, 5 divided by 5 reduces to 1. So f of g of x gives me that identity of x, which is a good thing. Half of our proof is done. But remember, we also have to show that the opposite composite, g of f of x, is also equal to x. So now we'll work on the second composite. We're going to start with the outside function again, which is our g of x function, the fourth root of 5x plus 2. This time underneath that fourth root, we're going to create a pocket for x. So we're going to have 5 pocket plus 2 underneath that fourth root. And we have to fill the pocket with the f of x function. So inside of my parentheses here is going to go an x to the fourth minus 2 divided by 5. I know it's probably a little tricky to read because it's so small. But we do simplify this next. So we can do the multiplication here first, and this is like a 5 over 1 times this fraction of x to the fourth minus 2 divided by 5. So we can cross reduce the 5's. So we have the fourth root of x to the fourth minus 2 plus 2. Doing the multiplication clears those parentheses. We've got some like terms here. The negative 2 and the positive 2 cancel each other out. So we have left now the fourth root of x to the fourth. And remember that a root undoes the power, so the fourth root and the fourth power cancel each other out. And our g of f of x composite also equals x. We just proved that the f of x function and the g of x function are inverses. They would undo each other. Okay, so why don't you guys take a few minutes and try doing the two composites f of g of x and g of f of x for example 8. The equations are a little bit more straightforward, and you guys should be able to help each other doing the composition. Good luck, and remember, I'll be back on Thursday to help and to answer any questions.